Design of a lightweight stream cipher, Bokhari 256. Abstract, symmetric key cryptography is the most commonly used primitive and stream cipher, in particular, meets the requirement of such algorithms. Developing a software-based synchronous stream cipher is reduced to building a pseudo-random sequence generator with specified cryptographic properties. It is pertinent to note that the implementation of such reliable cryptographic primitives is extremely complicated in practice that requires small processing capacity, low volume, low area, and low power consumption. In the recent past, a few lightweight stream ciphers have been implemented for real applications. In this paper, we have proposed software-based synchronous lightweight stream ciphers, Bokhari 256, mainly aimed for resource-constrained devices such as radio frequency identification devices, RFID, tags, wireless sensor node, WSN, and devices with limited processing capabilities, memory, power resources, and the limited computational unit, insufficient wireless bandwidth and low ability to communicate, and other general-purpose devices such as credit card, smart card, personal digital assistant, PDA, etc. Bokhari 256 has designed using the feature of some well-known stream ciphers like Fruit, Lizard, Sober and Grain 128 to improve the performance. The cipher Bokhari 256 uses a 256-bit key and initialization vector, 4, that is known to be safe and can withstand several cryptographic attacks. Bokhari 256 uses 8 variant stage LFSRs and a linear feedback function, for providing 256-bit security, while the internal states and bit permutation use commutation relations of bitstream over. We used some new design paradigm to fulfill the requirement of a low-cost environment as mentioned above. Keywords, Galois field, LFSRs, generator functions, cryptographic attacks, S-boxes. Introduction. As we know that a shift registers can be easily implemented by computer hardware due to their less duty cycle and synchronous behavior. A linear feedback shift register, LFSR, is used to generate a wide range of pseudo-random sequences, is the simplest type of feedback shift register. Because of LFSR linearity, knowing only output bits, we can test the LFSR using the algorithm given by Mundell, Kalikinkar, Zinks and Fan that generates any output sequence 1. Clapper and Gorski 2, 3 proposed a new type of pseudo-random binary sequence generator called feedback with carry shift register, FCSR. FCSR had a shift register, feedback function, and a small amount of memory. In addition to the current memory contents, the register bits are added to the number. The parity bit, depending on, of the total is fed back into the first cell, whereas the first cell is initialized with the higher order bits depending on the location of, are fed back into the first cell, and this new memory value is maintained for 33. The key component used in the design of Bokhari 256 is shown in figure I. The key parameters associated with FCSRs is relation integer, which is an odd positive integer. Z. It represents the number of register cells in the structure. Further, assume that equals, and is an odd prime number such that is the primitive, and, leaves remainder non-zero when is divided by, so the maximal run length of the period of this polynomial is found. The relation between the cardinality of the registers and the connection integer is exponentially dependent to one another and is given by equals. And this implies that plus equals. Mathematically, it is found that for any value of the expression plus is real, so it is better to accept the floor of this much amount. Hence the above relation gets expected value plus equals. According to Niederreiter and Harold, the notion of the key stream's 2ADIC complexity is also an important measure of the security of a stream cipher. 5. It is possible to increase the 2ADIC complexity of LFSR sequences by adding correct Boolean functions in the LFSR's output, but this issue has not received serious attention. Thus the purpose of this research work is to aim at exploring the possibility of designing a stream cipher model Bokhari 256 using LFSRs for resource-constrained devices and protocols like embedded binary HTTP, web HTTP, and compressed HTTP over PAN. Resource-constrained are likely to be extended to embedded computing systems implemented within the Internet of Things, IoT. Background study. In order to propose a lightweight stream cipher, the following lightweight cryptographic model of the ESTREAM candidates has been studied. Traditional ciphers for stream encryption and pertinent security issues are presented in 29. As referred in said work, ciphers Rivest Cipher 4, RC4, 30, A5/1 and E0 although not completely compromised, but they suffer from serious security issues and should not be used in new applications anymore. 31, 34. IJERT. In fast software encryption, FSE, Vahid Amin Ghaffari and et al. 6 have presented a new idea for the design of stream ciphers Fruit with a shorter internal state in 2015. Fruit uses a secret key not only in the initialization phase of the model but also in the key generation phase of the cipher. The Fruit is proven to be much safe and ultralight than grain. The main building block of Fruit uses linear feedback shift register and nonlinear FSR. The size of LFSR and NFSR is 80 bits and 64 bits long, respectively, while the internal state size of the cipher is found to be at least twice as of the security level required to resist the classic cryptographic attacks such as correlation attack, differential attack, side-channel attack, cube attack, time memory data trade-off attack. 6, 7. The main purpose behind this proposed model Fruit is to indicate how a secret key can be used to achieve minimal cost in terms of area, gate equivalent, efficiency and attack immune. The internal state of the Fruit is based on 43-bit LFSR and 37-bit NFSR, the left counter of 7-bit and an 8-bit right counter. The input vector of the Fruit is an 80-bit secret key and a publicly defined initialization vector of 70-bit long. Experimentally it has observed that the maximum number of key stream bits that can be generated from a single key and 4 is 243-bit long. 8. 2. Lizard. In 2017, Matthias Hammann, Matthias Kraus 1 and et al. 9 have presented a model Lizard, a lightweight stream cipher for power-constrained devices. Lizard, a lightweight stream ciphers for the energy-constrained environment as mentioned above. The hardware performance originates from a complex combination of a grain-like architecture, a newly proposed design principle for the state initialization of stream ciphers that offers confirmed security against TMD trade-off attacks aimed at key recovery attacks. Lizard uses 120-bit keys, 64-bit IVs, and has a total of 121-bit of internal state. The authors have also claimed that Lizard provides 80-bit security against key recovery and 60-bit security against any distinguishing attack. It is noted that the Lizard is only a unique LWC model that differs from the key length of the design paradigm that claims that the achieved security level is directly proportional to the key length of the cipher. 3. Sober. Sober is a family of stream ciphers originally developed by Greg Rose and ETAL-10 of Qualcomm Australia in 1997. The name is an artificial acronym for the Enabled Register 17-octet byte. The cipher was originally intended as a substitute for broken ciphers in cellular telephony. Sober was the first cipher, comprising a 17-byte linear feedback shift register, LFSR, a form of ruination called stuttering, and a nonlinear filter output. The shift register's specific design turned out to be vulnerable to guess and determine attack. 37. 4. The Grain 128. The Grain stream cipher was designed by Martin Hell, Thomas Johansson 1 and Willie Meyer in 2004. Their design is aimed at hardware environments in which there is very minimal gate count, energy consumption, and memory is there. It is primarily focused on 2 shift registers and a function of nonlinear output. The cipher has the upgrade option that at the cost of additional hardware the speed can be improved. 11, 37. The key size is 80 bits and no attack has been identified faster than exhaustive key search. The complexity and performance of hardware correspond with other hardware-oriented stream ciphers like E0 and A5/1 and are compare acceptable 12. The grain is a synchronous stream ciphers that operate on both LFSR and a nonlinear filtering function. It adopts a bit-oriented architecture, which is appropriate for constrained hardware implementations that produce one bit/cycle. However, it also offers the option to increase its speed by increasing the length of the processing word. Grain provides higher levels of security compared with the well-known A5/1 and E0 ciphers while providing small hardware complexity. It requires about GE for 1 bit/cycle and GE for 16 bit/cycle 13, 14. A software implementation is reported for the 1 bit/cycle rate that occupies 778 bytes of code and requires cycles for initialization and 617 cycles to generate the output. See Design Specification of Bokhari 256. In this section, we have described the design specification and key generation phase of the proposed model Bokhari 256. Design specification of Bokhari 256 mainly comprises 4 parts. Design taxonomy. The cipher Bokhari 256 is based on a single bit memory element and XOR operation, primitive polynomial over Galois field. Figure I represents key components used in this model 35. 2. The S boxes of Bokhari 256. Substitution boxes, S box, are implemented as search tables that map input bits to output bits. In block ciphers, they are a common and well-studied choice, hence I have used this method of design in the proposed model Bokhari 256. Some stream ciphers like 15, 16, 17 also uses S-boxes to improve their mapping nonlinearity behavior and mask the plain text bits with ciphertext. A special type of commutation relation-based S-box have used in this model. The sequence obtained from bit permutation box at each clock cycles is respectively. Since the next term of the sequence is unpredictable, thus it ensures that the next state of the S-boxes can't be determined. Thus the permit bits are secure under side channel and linear masking attack. Figure I key components of model Bokhari 256. 3. Key generation phase. In order to generate the key for encrypting the text, first, all the LFSRs are filled with their default seed value and reset to 0. After that, both polynomials, and, are filled with the binary stream equivalent to the polynomial. Equals, plus, plus, plus plus. Equals, plus plus. Which are equivalent to the seed. And. Respectively. At each pass of the outer loop, traverse with variable, the value attained by both the S-boxes is operated by commutation relation CR and this commutated value is further passed to each LFSRs. At each clock's duty cycle, the same process is repeated and at the end of the loop, 256-bit key stream is generated. The complete signature of the proposed algorithm is something like, where the symbol represents the multiplication operation of polynomials under Galois field. The multiplication operation is closed under the field containing elements. 4. Key for initialization phase. In this phase, the secret key, of 256-bit long, and the initialization vector, of 256-bit long, are loaded to the model and initialize the cipher to clock 8 times starting from 2. At each clock pulse, key stream bits and initialization vectors bitstream are produces for all equals. At each phase, bits pattern are produced by each. Thus times equals bit patterns are produced in each clock pulse. So a total of times bits pattern produces in a complete trigger comprises pulses that take initialization time. Cycle per bytes. D. Proposed model Bokhari 256. The main building blocks of Bokhari 256 are LFSR and Galois field, primitive polynomials over the Galois field, and a Boolean feedback function. The design specification of the cipher is used as a key stream generator that generates a pseudo-random bit sequence which is called PRNG36. At each clock's duty cycle, 8-bit key stream is XORed with an equivalent byte of plain text data to produce encrypted cipher text. Each element of can be reversed back to by using the same key stream with XOR operation. It is known that using a dimensional state transition matrix, a stage LFSR can be easily implemented to design stream ciphers. Such a matrix is called the LFSR state transition matrix. We also found that the characteristic polynomial, over Galois field, variable, the state transition matrix is closely connected to the cycle lengths of the generated PRNG, which is equal to, dash. Where is the number of shift registers 18. In the proposed model Bokhari 256, a new method of linearization for LFSRs, namely the basis Boolean network approach, is used 19 to define the output of the dependent variables. The Boolean function used in Bokhari 256 over dependence and equals is defined as, comma, 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 dash. Sad face, dot, dash, dash, dash. Bokhari 256 stream cipher uses a 256-bit key and 256 initialization vector. It routines on LFSRs of degree, comma, 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 and whose feedback taps are defined by the primitive polynomials, over Galois field. Two substitution boxes of order are used to achieve a proper mixture of bit patterns permutations. Bokhari 256 comprises two nonlinear feedback functions, and that are cyclically connected to each other. The state bit at the duty cycle oft clock is represented by the letter, whereas the whole state of the cipher at the same clock is referred. The feedback function, of all LFSRs behave linearly in each clock cycle, and the rest to nonlinear feedback function, and behaves nonlinearly for the same clock cycle. For different forthcoming phases of the cipher, the values of these two parameters get changed and functionality becomes nonlinear. So for different phases, the expression of the nonlinear feedback function changes depending on the values of min and maximum LFSRs, namely, comma, comma, 2. Each of them is associated with different primitive polynomials, defined over the Galois field, of degree, comma, 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 and, dot. Furthermore, an array of type integer is declared to specify the parameters for combining the lockup state of the LFSRs. At each clock cycle, the PRNG generates a random integer, such that, and the, comma, equals, it means the ordered pair, comma, are coprime in nature 32. For every set of LFSRs in the model, we have computed some value, equals, such that each is associated with the set of values are given in table I, equals. After getting the random value, an arbitrary integer, the initial state, seed, of the LFSR is computed. Period of the dash. Cipher generated by the proposed model is represented in table I. Period of the LFSR is calculated in MATLAB, so the average period of each LFSR is 9.65 bits per clock is found. In case of grain 12820, Sober 12821, BSF 12822, 23, A2U 224 and Hittag 25, 26, Cosmo 27, Fruit 8 and Lizard 28. The average period of dash bits generated by the LFSRs are as follows, refer to table I. Associated data processing phase. After the initialization phase of the keys initialization vector gets over, the cipher shifts to the next phase of their production are referred to as the dependent processing step. In this phase, the cipher takes the dependent data as input and updates the state of the cipher without producing output bits. The general procedure of the scenario is something like equals where denotes the length of linked data and represents the corresponding bits associated with linked data. Update the state in each clocking for equals 2 plus. The cipher continuously updates their state in each clock cycle ranging from equals 2 plus 2. Test vectors of Bokhari 256. Most stream ciphers are based on linear feedback shift registers, LFSRs, design that is less so in software, although they are powerful in hardware. Bokhari 250 SIXS design is based on LFSRs of stages each. For the state list, it uses 256 bytes, 2 S boxes each of 128 bytes of order, ranging from the memory location SBox L0 to SBox L127 and SBox R128 to SBox R255, and 32 bits of key memory ranging from 2, and the same initialization vector. The proposed model Bokhari 256 has run under the environment of JDK 1.6 and JRE on Windows 8.1 Professional in MATLAB. The following simulation results have obtained, refer to Table 2. The key stream and 4 are represented in binary form while the obtained cipher text is represented in hexadecimal and Unicode characters is given in Table 2. Table 2. Test vector result of Bokhari 256. Generated cipher text. Key/4. Example Dem 0. Conclusion. It is not a trivial task to provide a fair comparative analysis of the presented ciphers, as they are implemented in different platforms and the comparison metrics are not directly correlated. Nevertheless, in the case of hardware and software implementation of the proposed model Bokhari 256, the ciphers proposed by other authors also kept a restricted benchmark review. In performance metrics, number of clock cycles, processing time, throughput, efficiency and bits per cycle, the stream cipher Bokhari 256 found to be secure and appears to achieve better performance. After doing an extensive attack immune analysis, it has found that the proposed model Bokhari 256 can withstand many cryptographic attacks like guess and determine attacks, algebraic attack, side-channel attacks, the time memory trade-off with huge precomputation, correlations attack, and linear masking attack. The proposed model can be implemented in a real environment in order to achieve maximal performance.